In this video, I introduce a Metropolis-Hastings algorithm for machine learning. Metropolis-Hastings algorithm generates samples from a complex distribution. For example, we compute posterior P by sampling a complex function that includes likelihood and prior. Suppose Q is a candidate generating density and pi is the environment density distribution. A sufficient and necessary condition for a unique stationary distribution is invariable Markov chain. The goal of MH algorithm is to find a transition kernel sampling the state with high probability densities. For example, start from X1, we follow the uphill direction to sample the next state with a higher probability density. Before reaching the stationary distribution pi, if probability moving from state x to y is larger than probability from state y to x, namely we have this inequivalent equation. We define the probability of a move alpha to measure probability moving from state x to y. We select the probability of a move alpha using Markov property. We use this formulation to calculate alpha. If this denominator larger than 0, we pick a smaller number from these two terms. Otherwise, we let alpha equal 1 to construct an invertible transition. Suppose the invariant density pi is known and the transition kernel p is the unknown function to determine. Q and R are used to represent the transition probability P. Here, Qxy is the probability moving from state X to state Y, and R is a process remains at the current state X. The Rx is equal to 1 minus the probability over dy, not including this state X. We use two steps to generate a sampling sequence. First, select the arbitrary initial value x0, and then use the iteration procedure to generate the sampling sequence. Say we have x as the input, use q to generate a random state y, and use the function pi to calculate alpha. And then from uniform distribution, U to generate a random number U. If this alpha, for example, is 0.2, that means we only have a 20% probability use this new state Y as the next state. For example, we have alpha much smaller than the 1. That means this probability moving from state X to state Y much larger than the probability moving from state Y to X. That means the distribution is far away from a stationary distribution. However, the alpha increases as likelihood and prior are improved. That means the state distribution close to the stationary distribution. After this iteration procedure, we generate a sampling sequence x1 to xn. To get a sampling sequence independent of initial values, we discard the first k samples. The sequence from k plus 1 to n of likelihood and prior is the distribution of posterior p. For more details, please check with this reference. Thank you. Bye.